Have you ever pondered the infinite expanse of space and time and wondered, can they bend and warp like a piece of cloth? Imagine, if you will, a cosmos not fixed and rigid, but fluid and malleable, a universe where the very fabric of space and time is not an immutable entity, but rather a dynamic, ever-changing landscape. This is not the stuff of science fiction, my friends, but the very foundation of our understanding of the universe. Where once we believed in a cosmos as solid and unyielding as a block of marble, we now envision a universe as pliable as clay in the hands of a master sculptor. And who was this master sculptor, you ask? Who dared to challenge the conventional understanding and reshape our perception of the cosmos? Who dared to dream of a universe not of absolutes, but of relativity? Enter Albert Einstein, a patent clerk with an extraordinary vision. Albert Einstein, an unassuming patent clerk, was far from ordinary. His mind roamed the universe. Born in the late 19th century, young Einstein was known to be a dreamer, his thoughts often drifting towards the mysteries of the cosmos. His fascination with the universe was evident from an early age. The compass given to him by his father when he was just 5 years old set his mind ablaze with curiosity. He questioned the unseen forces that guided the needle, sparking a lifelong quest for understanding the fundamental laws of the universe. As he grew older, Einstein's fascination didn't wane. Instead, it intensified. He delved into the works of the great scientists of the past, trying to understand the nature of light and space. Isaac Newton's laws of motion and universal gravitation, James Clerk Maxwell's equations of electromagnetism. These were the intellectual giants upon whose shoulders Einstein stood. But as he delved deeper, he began to notice cracks in the foundation. Newtonian mechanics, the laws that so accurately described the motion of planets and apples falling from trees, seemed to be at odds with Maxwell's equations, which painted a picture of light as a wave moving at a constant speed. This was a paradox that puzzled young Einstein. How could light always move at the same speed regardless of the observer's motion? Why didn't these fundamental laws of physics agree? Einstein's struggle was a solitary one, filled with countless hours of contemplation and calculation. The world around him was oblivious to the intellectual storm brewing within this humble patent clerk. His ideas were radical, his methods unorthodox. But it was this very audacity, this refusal to accept the apparent inconsistencies in the laws of physics, that set him apart. And as he wrestled with these inconsistencies, a revelation began to take shape in his mind. A revelation that would challenge the very foundations of our understanding of space and time. A revelation that would forever change the way we perceive our universe. It was these inconsistencies that led Einstein to his groundbreaking revelation. In 1905, Einstein proposed a radical idea, the special theory of relativity, a theory that would not only change the way we perceive the universe, but also shape the course of modern physics. At its heart, the special theory of relativity is built on two fundamental postulates. The first is the principle of relativity, which suggests that the laws of physics are the same for all observers, no matter how they're moving or where they are. This means that whether you're sitting in a cafe reading a book or hurtling through space on a rocket, the laws of physics remain constant. The second postulate is the invariance of the speed of light. In other words, light always travels at the same speed, regardless of the speed of the observer or the light source. Imagine you're on a train moving at a high speed and you switch on a torch. The light from the torch won't add to your train's speed. It will still move at its usual speed, around 300,000 kilometers per second. This goes against our everyday experience and intuition, but that's what makes it so revolutionary. These postulates, though seemingly simple, have profound implications. They lead to the bizarre and counterintuitive predictions that time can dilate and lengths can contract depending upon the relative motion between the observer and the observed. It's a bit like a cosmic magic show where things aren't always what they seem. But unlike a magic show, this isn't illusion or trickery. It's the fundamental reality of our universe, as described by the special theory of relativity. Einstein's radical idea was met with skepticism initially, but as more experiments confirmed its predictions, it became a cornerstone of modern physics. It has deepened our understanding of the universe and laid the foundation for technologies we use every day, like GPS. But this was just the beginning. Einstein had a bigger theory in mind. Einstein was not content with his special theory. He had a grander vision, the general theory of relativity, an audacious leap of intellect. It's one of the most brilliant creations of the human mind. The general theory of relativity is a theory of gravitation, a description of how objects move under the influence of gravity. But it's not just any description, it's a bold new way of understanding gravity. In Einstein's world, gravity is not a force that pulls objects towards each other, like Newton proposed. Instead, it's a bending, a warping, a curvature of space and time itself, caused by mass and energy. Imagine a trampoline with a heavy bowling ball in the middle. The ball creates a dip in the trampoline fabric, curving it downwards. If you roll a smaller ball onto the trampoline, it'll naturally roll towards the bowling ball, not because there's a mysterious force pulling it, but because the fabric of the trampoline is curved. That's how Einstein envisioned gravity. Mass and energy warp the fabric of space-time, and objects move along the curves created. This theory replaced Newton's law of universal gravitation, which had reigned supreme for more than 2 centuries. It's not that Newton was wrong, but his description was incomplete. Einstein's general theory of relativity provided a more accurate, more nuanced picture. Here's the kicker, though. The general theory of relativity made some startling predictions. It suggested that the universe is expanding, a fact we only confirmed decades later. It predicted the existence of black holes, which we've only recently been able to observe. And it even explained the tiny shifts in Mercury's orbit that Newton's theory couldn't quite nail down. Einstein's general theory of relativity forever changed our understanding of the universe. It's a testament to the power of human curiosity, the drive to question, to explore, to understand. It's a reminder that sometimes to see the universe in a new light, we must dare to imagine the unimaginable. Einstein's theories have stood the test of time, shaping the way we perceive the universe and its mysteries. Just as a pebble creates ripples when dropped into a pond, Albert Einstein's theories have rippled through time, redefining our understanding of the cosmos. His work continues to shape the fields of physics and cosmology, offering profound insights into the very fabric of existence. Einstein's theories of relativity, both special and general, have been instrumental in predicting phenomena that seemed almost fantastical at the time. The concept of black holes, for instance, was born out of his revolutionary ideas. These enigmatic entities, regions of space where gravity is so strong that nothing, not even light, can escape their pull, were first proposed in his equations. Today, they are a cornerstone of astrophysics, with their existence confirmed by countless observations. Similarly, Einstein's theories have given birth to the concept of gravitational waves. These are ripples in the fabric of space-time, created by the acceleration of massive objects. Detecting these waves is akin to hearing the universe's symphony, allowing us to probe the darkest corners of the cosmos. The first detection of these waves in 2015, a century after Einstein first predicted them, was a momentous feat in the annals of science, affirming his enduring legacy. But perhaps the most profound impact of Einstein's theories is how they have transformed our perspective of the universe. No longer do we view space and time as static and absolute. Instead, they are fluid and dynamic, intertwined in an intricate cosmic dance. The universe is not just a stage where events unfold, but a dynamic participant in the cosmic ballet, its rhythm dictated by mass and energy. So next time you gaze at the night sky, remember Einstein's audacious vision. A universe where space and time are interwoven and malleable, forever dancing to the tune of mass and energy. Thank you for joining us on this journey through space and time. Until next time, keep wondering and keep exploring.